Welcome to today's Trane Engineers Newsletter Live program. I'm Jeanne Harshaw, and today we'll discuss acoustics for the indoor environment. We'll start the program by covering sound pressure versus sound power and how to apply them. Next, we'll discuss equipment rating standards to better understand how sound power data is obtained. And finally, we'll discuss two unique applications, classroom acoustics and open ceiling systems. To cover today's topic, we have application engineers Eric Sturm and John Murphy, and they are joined by acoustics engineer Derrick Knight. We'll start the program with John covering a few basics about indoor sound.
I'm going to spend just a few minutes on the fundamentals of sound so that we're all on the same page with terminology. Sound is the audible emissions that result from vibration of molecules within an elastic medium. Now, in the context of an HVAC system or a building, this elastic medium is either air or the building structure itself. It's generated by either a vibrating surface or the movement of a fluid. Airborne sound is transmitted away from a vibrating body through the transfer of energy from one air molecule to the next. The vibrating body compresses and expands the space between these air molecules. The pressure fluctuations that result from this repeated process take the form of a sine wave. The amplitude of the wave depicts pressure. The higher the amplitude, the louder the sound. Now, this transfer of energy takes time, and each complete sequence of compression and expansion constitutes a cycle. We use the term frequency to depict the number of cycles that occur within a second, the unit of measure being hertz. Now, if a sound occurs at a single frequency, it's called a pure tone. But typically, sounds are of a broadband nature, meaning that the sound is comprised of several frequencies and amplitudes, all generated at the same time. So the human ear can perceive sound over a wide range of frequencies. Measuring sound at each frequency would then result in a huge number of data points. So to make this more manageable, the full range of frequencies is typically grouped into smaller ranges called octave bands. Each octave band is defined such that the highest frequency in the band is 2 times the lowest frequency, and each is commonly referred to by its center frequency. For example, the 5th or 1000 Hertz octave band groups together sounds at frequencies between 710 and 1400 Hertz. Now, to describe the amplitude of sound at the different frequencies, we use 2 terms that are commonly confused: sound power and sound pressure. Sound power is the acoustical energy emitted by the sound source, expressed in terms of watts. It is not affected by the environment. Sound pressure is the pressure disturbance measured in the atmosphere, expressed in terms of pascals. Sound pressure is influenced not only by the strength of the source, but also by the surroundings and the distance from the source to the listener. Sound pressure is what our ears hear and what sound meters measure. A light bulb is a common analogy used to explain these 2 characteristics. Think of sound power as the wattage rating of a light bulb. Both measure a fixed amount of energy. Whether you put a 100-watt light bulb outside in your yard or in a closet, it's always a 100-watt light bulb and always gives off the same amount of light. Sound pressure is like the brightness emitted by the light bulb at your location in the room. This brightness depends on how far away you are from the light bulb, the color of the room, how reflective the wall surfaces are, and whether the light bulb is covered with a shade. These factors all affect how much light reaches your eyes, but do not affect the wattage of the light bulb. Similar to brightness, sound pressure depends not only on the sound power emitted by the source, but also on the characteristics of the surrounding environment. These might include the distance between the sound source and the listener, whether the room is carpeted or tiled, furnished or bare. Just as with light, environmental factors like these affect how much sound reaches the listener. While sound pressure variations in the air can be measured directly, sound power cannot. It must be determined by measuring sound pressure in a known environment and then calculating the sound power based on these environmental influences.
That was a great overview, John. As John said, Manufacturers often provide sound power data for their equipment, but the human ear hears sound pressure. So we need a way to convert sound power to pressure. And as an industry, we often want methods to further simplify how these sound pressure values are shared, published, and compared. So let's start there. To simplify communicating sound, we often use single number descriptors rather than octave bands. Examples include A weighting, C weighting, noise criteria, and room criterion. Of these, A and C weighting and noise criteria, or NC, are most common in our industry. All these descriptors share one thing. They all attempt to compensate for the non-linearity of how we hear sound. A weighting is a common single number weighting scheme. The blue line shows the standardized A weighting curve. Weighting can be applied to sound pressure and sound power, so it's important to understand the source of the underlying data. To use this curve, you start with octave band sound data. The curve, or table at the bottom, provides the amount to be added to each octave band. Notice that some are negative values. For example, we will add negative 26.2 decibels to the 63 Hz octave band value. Next, to produce a single number descriptor, each weighted value is logarithmically summed. Notice that the shape of the curve is such that the larger amounts are subtracted at lower frequencies. This compensates for the ear's lack of sensitivity at low frequencies. Also shown on the chart are the B and C weighting curves and their respective values. Here's an example. Octave band sound pressure from 63 to 8,000 Hz is given in the first row of the table. The A weighting factors are determined from the chart or table, then added to each octave. With each sum computed, these values are then logarithmically added. The sum is 52.8 dBA, but we'd round it to 53 dBA. The same octave band sound data can be C-weighted with their respective weighting factors. The procedure remains the same. With each sum computed, these values are then logarithmically added. The sum is 65.5 dBc, rounded to 66 dBc. So the same sound data can be A-weighted, with the result being 53 dBA, and C-weighted to 66 dBc. And remember, weighting can be applied to both sound power and sound pressure. Now there's another important aspect to weighting, and that's data presentation. We started with octave band sound data, then applied a weighting procedure to simplify this data to a single number descriptor. Sometimes people mistakenly display the data shown in the sum row. This is misleading because it's not the actual octave band sound power or pressure. This is just an intermediate step in the weighting process. So when using these weightings, you should only show a single value, not the intermediate octave band data. Next, let's look at noise criteria, or NC. This single number descriptor can only be applied to sound pressure. This NC chart includes a series of curves that correlate to different NC levels. Notice the upward sweep of the curves in the lower octave bands. That's to accommodate the ear's reduced sensitivity at lower frequencies. To calculate an NC value, simply plot your octave band sound pressure data. Whichever data point crosses the highest NC curve sets the NC value. In this example, the sound pressure at 63 and 125 Hz just intersect the NC40 curve. So we'd call this NC40. The major complaint about NC curves is that they don't tell anything about the quality of the sound spectrum. The new red line shows another data set plotted on the NC chart. Here, the NC40 curve is the highest crossed, but this time the NC is set in the 4000 Hz band. Both the blue and red curves would be reported as NC40, but they would sound very different. If you were to listen to these two spectra, the blue one would probably be described as rumbly, and the red one as staticky or having a lot of hiss. Neither would be very pleasant. A sound spectrum that more closely follows a single NC curve will sound much more pleasant. Next, let's look at how to convert sound power to sound pressure using the source path receiver method. This method describes the three important components of an acoustical model. First, the source creates the sound. It might be a chiller, air handler, a rooftop, terminal unit, or other noise-generating piece of equipment. Sound can travel between a source and receiver along one or more paths. A path accounts for everything that affects the sound as it travels from the source toward the receiver. And the receiver is where we hear the sound. This could be indoors or outdoors. To determine the total sound, we need to sum the sound paths. What is computed, it is often compared to a sound target to determine whether the sound meets the owner's requirement or project goal. If not, revision may be needed. Sound targets can come from a variety of authorities or publications. Examples include AHRI's HVAC Applications Handbook, which includes the Noise and Vibration chapter. In this chapter, Table 1 provides reference NC values and approximate overall sound pressure requirements in A and C weighted values. Standards, such as AHRI's Standard 189.1, include acoustical sound targets for specific space types. In addition, there are unique requirements for classrooms and learning spaces in Acoustical Society of America's S12.60 standard. Later in the program, Derrick is going to discuss this standard in greater detail. And some rating programs like LEED or the Well Building Standard include acoustical requirements. And finally, some local jurisdictions may have acoustical sound targets. Most often, these targets are in the form of outdoor lot line sound ordinances to ensure neighboring property sound is acceptable. Let's look at an example of how source path receiver is applied. Here's a package DX unit installed just outside of the occupied space. This is our source. Sound travels from the unit through the wall into the space. Additionally, sound travels through the supply duct system and return air system to the space. Sound inside of the duct system can break out from the sheet metal into the plenum, then into the space. There are 5 potential sound paths from the source to the receiver. An acoustical model can be made to predict the overall sound pressure level in the space by analyzing each path, because each path will have a different effect on the overall sound. When selecting a receiver location, it's typical to adopt a worst-case mentality. That is, if a sound target is set for a room, look for the place in the room where the HVAC system will be the loudest. Sometimes, practitioners will ask for a sound target. What is the sound pressure goal for the space? The target can be expressed as octave band sound, but that can become cumbersome. So it's very common to use the simplified methods to describe overall sound, like NC, A, or C weighted. Now, with each path independently computed, logarithmic addition is performed to determine the overall octave band sound pressure. This value is then compared against the sound target to determine pass or fail. To obtain package rooftop sound data, we'll need to consult the equipment manufacturer. Usually, sound power is available through a product catalog or selection program. Notice that there are 3 different sets of data here, ranging from 63 to 8,000 Hertz. Ducted discharge, which is the sound power at the unit discharge. Ducted inlet, which is the sound through the return, and outdoor, the sound coming from the rooftop casing. Derrick will discuss how all of this sound data is obtained later. Software can make this acoustical modeling process a lot easier and faster. For this, I use the Trane Acoustics program to calculate the individual sound paths, and there are other software programs in the market too. Now, each sound path can be modeled. What you see here is only one path, the supply airborne path. And the progression is from sound source to receiver. First, unit ducted discharge sound power data is entered. Then, every element within the sound path is described with details like dimensions, materials, and acoustical treatments. The next element is the straight duct leading out of the rooftop to the elbow turning upward. Then, straight duct and another elbow turning back into the building, leading to another section of straight duct. Some air leaves the supply duct system through the first junction, while the rest of the air leaves through the second junction. Air passes through flexible duct connections, then a diffuser into the space. The sound is corrected for the indoor environment, like dimensions, ceiling materials, floor coverings, and furniture. And here, the presence of 2 diffusers is noted. Throughout, the software has been performing logarithmic addition and providing summations with a final sum. This is the octave band sound pressure in the space for this single path. So we started with sound power, then applied power to pressure transfer functions in software to determine sound pressure. The program uses empirically derived equations to compute the sound pressure using all of this information. Each path is independently calculated and displayed. Then, each path is logarithmically summed to determine the overall space sound pressure. So, in the 63 Hz band, the logarithmic sum of 39, 51, 45, 49, and 39 is 54 decibels. We can quickly see which path is dominant or which octave band is causing the highest sound pressure. Looking at the data, both the supply and return airborne paths are dominant. The octave band sound pressure in the sum row can be A and C weighted, with the results being 45 dBA and 57 dBc. I've included those examples in your handouts. And the octave band sound pressure can be plotted on the NC chart, with the result coming out to be NC39. We can also look at how well the sound pressure correlates to the NC curve sweep. This one is okay, but we could revise and do better. Software can quickly calculate these single number descriptors for us. Next, Derrick is going to discuss how equipment sound data is obtained.
Now that we understand how sound power data is applied in building design, let's explore the common equipment sound rating standards. Sound rating standards are published by AHRI, which is the American Heating and Refrigeration Institute. Acoustic engineers from member companies collaborate on these standards to provide valuable sound information useful in both direct equipment comparisons and building design. In this segment, we will discuss the sound rating standards which are useful to indoor sound, which includes AHRI 350, 260, 880, and 885. Standards 350 and 260 cover non-ducted and ducted HVAC equipment, respectively. 880 is a performance certification program, which includes acoustics and also specifies how manufacturers can publish NC ratings of their terminal products by utilizing methods outlined in AHRI 885. Now that's a lot of letters and numbers to throw around, but don't worry, we'll review them in enough detail for you to understand how they are useful in designing quiet spaces. Let's begin with AHRI 350, which describes the method manufacturers use to measure and publish sound power ratings of non-ducted indoor HVAC equipment. The scope of this standard includes, but is not limited to, fan coils, air source unitary heat pumps, water source heat pumps, packaged terminal equipment, and VRF systems. Basically, any HVAC equipment that conditions the space without ductwork. It's important to note that many of these equipment types have both indoor and outdoor components. Standard 350 only covers the indoor portions. We covered the topic of outdoor noise in a previous program, and a link to it is provided in the bibliography. Comparing and contrasting is a great way to better understand things. Here we will compare AHRI 350 to non-HVAC sound standards. Many products emit sound in a way that is important to customers. As such, most products have their own sound standard. Vacuum cleaners, blenders, projectors, and computers are just a small sampling of products with sound standards dedicated to them. Generally, these products will begin with a sound power measurement very similar to standard 350, but the data which gets reported to the customer is often very different. Some products will report values as overall A-weighted sound power. Others might calculate a predicted sound pressure level value at a user-relevant distance. The decision on how to report sound to customers is sometimes well coordinated by each industry, but sometimes not. The fact that both sound power and sound pressure use the decibel can lead to further confusion. We hope that after this episode, you will understand how sound power is a property of the sound source, while sound pressure depends on both the source and the installation. The method of measuring and reporting sound in AHRI 350 is perfectly suitable for many other types of products. Like many other sound power standards, 350 sums the total power emitted and optionally reports the overall A-weighted sound power level, which can be useful when doing an A-B comparison between two units doing the same job. For example, if these two fan coils both meet the design requirements, choosing the one with the lower overall A-weighted sound power will be the quieter choice. Note, however, that this does not tell you what the resulting sound pressure level in the room will be, so you won't know if you will meet the acoustical requirements just by doing this A-B comparison. Fortunately, standard 350 requires more detailed reporting than many other product sound standards. Unlike a vacuum cleaner, the person who experiences the sound of a fan coil won't be the person who is paying for the fan coil. The relationship between listener and customer is complicated and often convoluted in commercial buildings. Therefore, the industry standard is to provide octave band sound power data so design professionals can make informed decisions on behalf of the people who will be using the space. In an earlier segment, Eric showed us how the octave band sound power data can be used to evaluate a room to meet a specific background noise requirement. When you receive 350 sound power data, there should be supporting documentation which clearly defines three critical variables which are fundamentally tied to the amount of sound the unit emits. First up, the unit operating point, which includes the airflow, fan speed, and static pressure rise. Second, the unit configuration, which varies greatly. But just for example, we are showing a fan coil in 3 of the many possible configurations. On the left is vertical cabinet. In the middle is horizontal concealed. And on the right is vertical recessed. And third, the unit installation. Shown on the right-hand side of the slide is an example installation of a horizontal concealed unit. Let's continue to use the fan coil product family as an example to walk through how these 3 variables are related to sound. In a fan coil, the primary noise source is the fan. The relationship between the fan's operating point and sound is intuitive. Increasing speed and flow will increase sound. Customers will select fan coils based on the flow required in the room. But the unit configuration and installation can impact the operating point too, meaning the 3 sound critical variables are not independent of one another. A fan coil's configuration can include number of rows of coil, various filter options, inlet airflow direction, and discharge airflow direction, among others. Each of these choices will impact the operating point of the fan. For example, choosing a filter with higher pressure drop will increase the internal losses of the unit. To deliver the required airflow, the RPM of the fan will have to be increased, which increases the sound. However, these options can change the sound in other ways. For example, when the airflow into the unit changes directions, this can impart different patterns of airflow into the fan and alter the sound even if the operating point doesn't change. And if that isn't convoluted enough, we have unit installation to consider as well. Fan coils are installed in many ways, but for non-ducted fan coils, we will reduce the complexity to 2 variations. Cabinet units will be installed along a wall or ceiling. Typically, they have more aesthetic finishes because people will see them as part of the room. The other variation shown here is concealed. Concealed units are furred in, so everything is hidden from sight other than the inlet and discharge louvers. The relation to sound here is important because for a cabinet unit, the sound which breaks out of the unit casing is often significant enough to add to the sound coming out the discharge and inlet openings. For concealed units, the additional layer of drywall may eliminate or at least significantly reduce this radiated portion of sound. Standard 350 covers all of these variations. When concealed units are tested, they are enclosed in drywall similar to how they will be installed in the field.
This sounds like a lot of variations to keep track of. So how do manufacturers manage all this complexity?
That's a great question, John. Once we consider all of these variables, it is common to find that a product family has millions of acoustically significant variations. Most manufacturers manage this by providing the relevant sound data through their product selection software. However, a very small sampling of data is often published in online documents or product catalogs. Care should be taken when comparing data to ensure a fair A/B comparison is being made. Next, let's discuss AHRI 260. The scope of 260 does not call out specific product types. Instead, it simply says it applies to any ducted equipment containing fans. Most equipment types, which fall under the scope of Standard 350, are also available in ducted configurations. All of the operating point, unit configuration, and unit installation variables are important to Standard 260 as well. But here we have an entire standard that is just like Standard 350, only with the addition of ducts. This suggests the ducts are a significant addition to HVAC equipment when it comes to sound. Let's explore why that is. Let's think back to what Standard 350 measured and why. It sums all the sound energy emitted from a unit. This data is useful in 2 ways. First, it allows for fair A/B comparisons of sound between manufacturers. Second, it allows knowledgeable designers to calculate the sound pressure level in a room and determine if it will meet the design criteria. But if we add 1 or more ducts to a unit, some of the sound energy is directed away from the unit, and that sound travels through its own unique path from source to receiver. If we just wanted an A/B comparison, we could use Standard 350, add the ducts, and measure the sum of the sound power. But this information would be insufficient for sound pressure evaluations. This is why AHRI 260 exists. It tells manufacturers how to break up the sound power emitted by the units into sound power components, which facilitate design. Let's take a look at the sound power components defined in AHRI 260. For the ducted discharge component, the discharge duct is connected to the sound chamber. To achieve various operating points, additional ductwork can be attached to the inlet for throttling, or the chamber can be equipped with a wind tunnel. Keep in mind that each of these sound component setups will be tested at enough operating points for manufacturers to predict sound at all operating points. A similar setup is used for ducted inlet. Note that the inlet duct is now directed into the reverberation chamber. And again, many operating points will be measured in this setup. In casing radiated, the unit is placed inside the chamber. and both the inlet and discharge are ducted out of the chamber. Extra layers are added to the ducts to ensure only the sound radiated directly from the unit casing is included in the measurements of each operating point. Free inlet plus casing radiated removes the inlet duct from the casing radiated setup. Note that the lack of an inlet duct significantly changes the airflow into the fan, which changes the sound. In other words, the free inlet plus casing radiated component will not be equivalent to adding the previously defined components, ducted inlet and casing radiated. And finally, the free discharge or free inlet setups are less common, but in these cases, the unit is installed just outside the chamber and sound power is measured on the non-ducted side. It's also helpful to know that when manufacturers report AHRI 260 sound power data, they will only include the components relevant to the unit as selected. For example, if an air handler is selected with a free inlet, the reported sound would only include the ducted discharge and free inlet plus casing radiated components. These specific terms are also often shortened or abbreviated. It's not uncommon to see ducted discharge shortened to discharge, and free inlet plus casing radiated to be shortened to radiated. Now, let's take a look at some sound data for an air handler. When a ducted unit is selected at a particular operating point in a specific configuration, the resulting sound power components are reported by the manufacturer relating to that specific selection. This set of data then becomes the input to the type of analysis shown earlier, which allows for prediction of the resulting sound pressure level in a room after accounting for all sound paths. AHRI 880 is the standard used to measure and report performance of variable air volume terminals. This product category has a certification program which audits units from all participating manufacturers. Standard 880 covers all VAV boxes, but not all VAV boxes are part of the certification program. The certification program is a large topic in and of itself, so we are going to just focus on 880 as it relates to sound data. Sound performance requirements are specified through a combination of pointing to other standards or specific sections of other standards and defining some of the technical requirements in the body of 880 itself. Like Standard 260, 880 specifies sound power components. The majority of VAV boxes are configured such that discharge and radiated sound power components apply. Exhaust units are covered by 880 as well, but much like the free discharge or free inlet in AHRI 260, this component is only included here for completeness, as it is rare.
When comparing this to the other indoor sound standards Derrick explained, you'll see that Standard 880 covers a more limited range of frequency bands. Standards 350 and 260 cover 8 octave bands from 63 to 8,000 Hertz, while 880 covers just the middle 6 bands from 125 to 4,000 Hertz.
That's right, but the wider range in 350 and 260 is not prescriptive. Manufacturers sometimes choose not to publish data in the 63 Hertz band and/or the 8,000 Hertz band because for some products, the sound energy in these bands is negligible. While we are thinking about how Standard 880 compares and contrasts to 350 and 260, let's review the important concept of sound power components. Recall that AHRI 350 does not break up the sound power into components. And this is very similar to how many non-HVAC products report sound power. Therefore, we will get a single set of octave band sound power values. AHRI 260 defines 5 sound power components, but only the relevant components relating to the product configuration will be reported. Standard 880 defines 3 sound power components, but most units will be configured such that only discharge and radiated apply. Now that we've covered all of the indoor sound power standards, we will finish our discussion with Sound Application Standard, AHRI 885. The scope of the standard considers terminal devices, specifically VAV boxes. The calculations begin with standard 880 sound power values, functions for ducts, plenums, turns, diffusers, and rooms are provided. It essentially does on paper what Eric showed us using the Trane Acoustics program. The calculations assume the sound coming from upstream is significantly less than what is coming out of the terminal device. While the standard was clearly written around VAV boxes, the functions would apply to other terminal products. And there are currently efforts underway to expand the scope of A85 to include fan coils and water source heat pump terminal devices. This standard is just over 60 pages long, but there is one page in the standard which is referenced more than any other. Appendix E contains a table of 4 power to pressure transfer functions. These transfer functions reduce multiple installation functions into a single combined effect. However, the physical meaning of this standard installation is not documented and is lost to history. Additionally, some of the AHRI equations have been updated with new research, and the functions would no longer agree with the hypothetical installation in any case. In addition to having no description of what type of installation will yield these effects, the calculations of NC are done on discharge and radiated components separately. This is not how one predicts the NC level of a real room, where you sum the various sound paths prior to calculating the NC rating. Therefore, the published NC ratings of HVAC equipment are only suitable for A/B comparisons and should never be used to predict the sound pressure level in a real installation. It is not known how the published NC rating would relate to your specific application. In summary, we have taken a deep dive into 4 AHRI sound standards. Let's review what we have learned. Standard 350 sums all of the sound from non-ducted products and reports the values in up to 8 octave bands ranging from 63 to 8,000 Hz. It additionally provides an option to publish a single number value, the overall A-weighted sound power. Standard 260 breaks the sound power into sound power components. It defines 5 components, but only those relevant to a particular selection will be reported. The frequency range is the same as Standard 350, but it does not define any single number descriptor of the values. Standard 880 defines 3 sound power components, but only requires data to be published in 6 octave bands from 125 to 4,000 Hz. Standard 885 defines the equations needed to predict a sound pressure level in a room for terminal devices. Appendix E is widely used to publish NC ratings of terminal devices.
A great deal of change is underway with regard to classroom acoustics. So next, Derrick will cover some history and recent developments.
In this segment, we will provide a brief historical review of classroom acoustics, review the HVAC noise requirements relevant to classroom acoustics, and discuss the current state of classroom acoustics as it relates to building codes. The Acoustical Society of America, ASA, began working on classroom acoustic standard in the mid-1990s. While it seemed obvious that communication between a teacher and students was a prerequisite for learning, almost no codes throughout America addressed this need. The ASA gathered experts and launched working group meetings in 1994. Approximately 150 professionals throughout the field of acoustics contributed to the standard. The group included representation from academia, industry, and practitioners with expertise in noise, speech, language, hearing, and architectural acoustics. By 1998, the Federal Access Board had been swayed by a parental appeal in relation to hearing in classrooms and backed the efforts at the ASA. The standard was first published in 2002. 2 corporate sponsors allowed for the standard to be downloaded for free for over a decade. The original goal was to create federal regulation, but this eventually shifted to influencing building code. In 2017, the core requirements from S12.60 were adopted in the International Code Council's Accessibility Code to provide requirements for enhanced classroom acoustics. More recently, these requirements were rolled into Model Building Code IBC 2021 to apply to all classrooms. This version of IBC is currently being adopted state by state, and some of you may have already run across this requirement filtering into your local building codes. Standard S1260 defines the background sound pressure level limit in classrooms using two metrics, 35 dBA and 55 dBc. These same background noise requirements were adopted into IBC 2021 for all classrooms less than 20,000 cubic feet in volume. Recall from our earlier learning that weighting networks are often applied to sound pressure measurements to mimic the ear's frequency-dependent response to sound. The A-weighted network best fits the human perception of sounds by weighting the middle and high frequencies over low frequencies. However, this can sometimes allow for noise sources with substantial low-frequency sound energy to adhere to the dBA requirement while creating an uncomfortable amount of rumble. The 55 dBc requirement ensures this does not slip through the cracks. Earlier in the program, Eric showed us how one can predict the sound pressure level in a room using a tool like the Trane Acoustics program. The input to that tool is sound power measured in accordance with one of the AHRI indoor sound power standards we reviewed in the previous section. So, by using all we have learned today, you can design a classroom which meets current or upcoming building codes and supports learning in accordance with guidelines developed through consensus among professionals throughout the field of acoustics. If you would like to see an example of predicting and measuring HVAC noise in classrooms, refer to the bibliography in the handout material for a link to the Trane white paper titled Achieving Acoustical Standards in the Classroom.
There's been a growing trend to provide open ceilings in buildings. This can open up the building and provide a more industrial look, showing some cool stuff. To achieve this, acoustical ceiling tiles are omitted from the design. Now, as the name implies, acoustical ceiling tiles help attenuate noise-generating equipment in the plenum. They are also used to conceal overhead, mechanical, electrical, and plumbing equipment from view. And the tiles provide a physical barrier that separates the occupied space from the plenum, which is important if the plenum is used as a return air system. High-density acoustical ceiling tiles can provide significant sound transmission loss, even in the difficult-to-attenuate lower octave bands. Here's an example with a ceiling-mounted piece of equipment. This could be a VRF terminal or branch controller, water source heat pump, fan coil, or, as shown in this example, a VAV box. This terminal unit produces discharge sound, which passes through the ductwork system, through the diffusers, and into the occupied space. The terminal also produces radiated sound, which radiates into the ceiling plenum. Some duct systems may also produce breakout noise, which also radiates into the plenum. When acoustical ceiling tiles are present, much of this radiated noise can be attenuated and reduce the total transmission to the space. If the acoustical ceiling tiles are removed, in our example, the sound attenuation in the plenum is significantly less, which results in more sound in the occupied space. Compounding this, hard reflecting surfaces like exposed concrete decking can reverberate this and other sounds. This can result in additional HVAC noise in the space, with the overall background noise louder, which might make it more difficult for occupants to communicate and concentrate on tasks. Let's look at an example. Here, we have a 1000 CFM series fan-powered VEV terminal installed above a space. Conditioned air from an air handler or rooftop is delivered to the VEV box. The terminal fan continuously operates to provide conditioned air to the served spaces. This is intentionally a very challenging application due to the presence of the terminal fan. Here's the sound power and NC data from the selection program. Notice that we have multiple sets of sound data corresponding to the VEV box discharge, radiated from the casing, and radiated from the plenum inlet. As Derrick explained before, the selection program provides NC values for each path based upon transfer functions from standard 885. But this example installation is different from the assumptions made in that standard, so these NC values do not apply. And As Derrick told us, it wouldn't make sense to have different NC values for each sound path. So we can use software to evaluate and compute the sound pressure for each sound path. First, let's look at the system with acoustical ceiling tiles in place. The discharge sound pressure was computed for the first and second diffusers, the duct breakout into the ceiling plenum to the space, and the radiated sound into the ceiling plenum to the space. The resulting space sound pressure was NC32, or 39 dBA, 51 dBc. This is pretty good. The challenge comes when the acoustical ceiling tiles are removed. The system can be re-evaluated without acoustical ceiling tiles. Removing the tiles results in a significantly louder installation. Now, the sound pressure is at NC51, or 57 dBA, 63 dBc. It might be easier to visualize this. First, let's look at the discharge of the two diffusers. The two red lines represent the two diffusers installed with acoustical ceiling tiles, while the data in orange shows the system without tiles. There's a slight difference. The system without tiles is a little louder because there's less absorption in the space. And here's the radiated noise from the terminal box into the space. The system without acoustical ceiling tiles in orange has a much higher sound pressure because there's nothing to attenuate this radiated sound. And duct breakout is attenuated well by the acoustical ceiling tiles. But remember, we don't hear sound paths separately, but rather the sum of the paths. So here's the sum of the individual paths. The system without acoustical ceiling tiles in orange is louder, and much of that is driven by the radiated component. Again, this represents NC51, which is likely too loud for many space types. So the question is, what can we do? There are several options that are available to us with the open ceiling system. First, the VEV box manufacturer offers a factory-installed and tested attenuation package designed to reduce radiated sound. The data in green shows the VEV box with factory attenuation. This is an improvement over the standard terminal box installation without acoustical ceiling tiles. But NC44 still may not be good enough for the space type. Another option might be to relocate the VEV over a non-critical space, which also includes a ceiling plenum and acoustical ceiling tiles. Now, the radiated sound will be better contained to the ceiling plenum of this adjacent space. There still is an opening in the wall allowing air to flow from the occupied space to the non-critical space plenum. Viewing the NC chart, we can see that relocating the terminal unit helps, as shown in light blue. Now, the space sound pressure is at NC41. Remember that there's a small opening in the wall to allow air to transfer into the plenum for recirculation by the series fan-powered VEV box. We can improve this by adding a small section of acoustically lined ductwork to further reduce the radiated sound being transmitted into the occupied space. And much of this radiated sound comes from the series fan-powered VEV box inlet. The dark blue line represents this installation. While this isn't quite as good as the original installation with acoustical ceiling tiles, NC32, it is very close at NC33. This is a difficult example because the terminal has a small fan, which makes noise. But we were able to achieve similar sound levels by performing a what-if analysis using software. So, what if we install that attenuated VEV box over the adjacent space and use the short, lined return duct to further reduce radiated sound? The purple line represents this installation. Notice how the purple line is nearly atop the previous configuration in dark blue. When simplifying the octave band data to single number descriptors, the results are the same as well. NC 33 or 40 dBA, 51 dBc. You can see that the octave band is not exactly the same, but it's very close, and those details are lost in the simplification process. So why didn't the attenuated box provide better space sound? Here's what happened. The radiated path has been quieted, and the other paths, diffusers and duct breakout, have now become the dominant paths. To match the original installation with acoustical ceiling tiles, we'll now need to turn our attention to attenuating the ducted discharge and breakout paths. Acoustical modeling can help us analyze different scenarios and choose the best attenuation mechanisms. But it also allows us to see what might be excess or unnecessary. Now, another popular option is to incorporate acoustical panels, baffles, or clouds to add some aesthetically pleasing attenuation while also keeping the open ceiling concept. These panels may be mounted to the wall or suspended from the ceiling. Okay, let's look at just one more iteration. Here's one of the previous examples we looked at, where the light blue line represents a relocated terminal unit over the supply closet. The indigo night-colored line shows how adding some absorption in the form of acoustical clouds impacts the overall sound pressure. At mid and upper frequencies, the impact is apparent. This helps if the project goal is to limit sound pressure to NC 40 or lower.
As Eric demonstrated, the design team has some options when trying to comply with an indoor sound target. Acoustical predictions made through modeling can help evaluate different options and inform the team on which would work best. Now, I think it's worth noting that this example is one of the most challenging applications for a space with an open ceiling, since a fan power VV box contains a noise-generating fan located very near the occupants. Another option might be to revisit why a fan power box was chosen to begin with. Now, historically, series fan power VV boxes were often used to maintain a constant CFM of air circulation to the space. But more recently, designers have trended toward variable speed fan control to reduce energy use. If a constant CFM is not needed, it might be prudent to instead use a single duct VV box without a fan. By using the dual maximums control sequence, this type of box can now deliver the higher CFM desired during heating mode while avoiding the noise of the terminal fan. Let's hand it back to Jeanne to wrap up.
That is a lot of great information. Octave band sound pressure, ranging from low to high frequencies, is heard by the human ear. But for equipment, sound power is usually provided. Sound power is unaffected by the environment. There are different single number descriptors used to simplify sound data, with the most common being A and C weighting and noise criteria. There are many different standards developed by AHRI to determine equipment sound power. This can be useful for acoustical analysis using the source path receiver method. AHRI 350 is used for indoor non-ducted HVAC equipment. Standard 260 is used for ducted equipment, 880 for air terminal units like VAV boxes, and standard 885 provides procedures for estimating air terminal sound pressure levels in spaces. Classrooms have a unique set of requirements that are starting to appear in model codes. And finally, open ceiling systems can present acoustical challenges when sound-producing equipment is installed nearby, but there are usually ways to mitigate the sound. Consider evaluating all of these to determine how to best achieve the acoustical target. So that's our program on acoustics for the indoor environment. We hope you found it a helpful way to learn about this subject. As always, the bibliography included in your handout provides more information on where to find a number of resources related to today's topic. Or contact your local Trane account manager for specific information on Trane systems, equipment, controls, and services. For those of you seeking continuing education credit, check out the newest self-paced online courses at the Trane Education Center. Finally, for those of you viewing in person, please fill out a survey and let us know what you thought of today's program. Thanks for joining us today. We look forward to seeing you next time.